Hello everyone and welcome to a new episode of our 125 years Belgica vlog. And in this one, my colleagues of the marine geology team and me will explain to you what we're actually doing on this Polarstern expedition. So our objective is to reconstruct the glacial history of the Bellingshausen Sea along the west coast of Antarctica. And we do this by visualizing and sampling traces of the last ice age on the seafloor. Ultimately, we strive to reconstruct the pattern of retreat of the Antarctic ice sheet after the last ice age. And during this episode, you will meet the various members of the marine geology team as they will each explain one of the steps of our research. And up first is James in the geophysics lab.
So this is the bathymetry lab, which is one of the most important rooms on the ship. And here we are releasing pulses of sound from the base of the ship, which travels through the water column to map the structure of the seafloor beneath the waves here as we're going along. And this is important because we are mapping buried or ancient glacial landforms that record how the ice was flowing in the past, and we can use that to understand what's happening beneath the ice today. On the other side of the lab, we have the sub-bottom profiler, and this is similar in concept to the multi-beam bathymetry. So we emit pulses of sound, which then travel through the water, but these have a slightly lower frequency that allows it to penetrate under the seafloor and reveal all the buried layers beneath. And these are really important for choosing our core sites because we can see how much sediment is left under the seafloor to then target. And we've got a fantastic example here of how we've chosen 3 of our core sites based on these thick packages of sediments which reveal past environmental conditions that we can use to reconstruct ice retreat patterns.
We collect our sediment cores using this device here, the gravity core, and its name says exactly what it is. So it consists of a hollow metal barrel between 3 and 15 meters long, and on the inside there's a hollow plastic liner. On the top of the gravity core there's a 2-ton weight head. And when we collect sediment cores, we lower the entire gravity core using a winch through the water column and towards the seafloor. When it reaches the seafloor, it will penetrate through the various sediment layers under its own 2-ton weight. And when we retrieve the core back on the ship, the plastic liner inside will be filled with sediments. We specifically focus on locations where we can sample glacial sediments which were previously deposited below the Antarctic ice sheet during the last ice age. And more specifically at locations where they transition into more recent marine proglacial sediments which were deposited in the Bellingshausen Sea. Because by studying these sedimentological transitions, we can reconstruct how the Antarctic ice sheet retreated after the last ice age.
How does it look?
Oh, pretty much full.
Basically it's full to the top.
Look, take a look in the
barrel.
Welcome to the multi-sensor core logger lab. Here we log the cores. This is like the first step after the coring process. And we measure different physical properties. For example, the core thickness, speed of sound through the sediment, the density, and magnetic properties. And with that, we can do like first estimations of the sediment in the core. For example, where it comes from. Is it more a subglacial sediment? Because then the density would be higher and the magnetic properties would also be higher in comparison to like marine sediments. There we would see like a different trend. And yeah, with that we can look kind of inside of the cores and see which cores we should open first.
Alright, so the next step is to split the cores and as well as measure some shear strength within the cores and take some subsamples. So let's head on over to Wet Lab 2 where we do all this stuff.
Describing the core, and there's an interesting section of glacial marine sediment that we recovered from the working area we are in right now, and what you nicely can see is the transition here from subglacial sediment, so where the glacier was sitting on and compacted the sediment, into less compacted sediments with this color change into more greenish colors towards seasonal open marine sediments, so to the environment what we see today in the working area. We summarize all that in a so-called core description, and this is what we do here on this tablet. And so in a very descriptive way we look at this section and describe in a relatively simple way what we see, but of course with all the necessary details. And this is summarized here, and so when afterwards colleagues also want to look at what we recovered here in the region, then they can immediately see what we got and what we were working on.
Take our subsamples, we'll take some of these subsamples back to our university labs where we'll measure some additional parameters such as water content, biological sampling, and grain size analysis. And then this is really important because these parameters help us differentiate between marine sediments and glacial sediments.
So another crucial step is the identification of microfossils in our sediment cores, and we specifically look at which species are present and how they are distributed through the sediment cores. And we specifically look at two types of microfossils, and this is what Zelna is going to explain to you in her lab.
Hello, welcome to the microscopy lab. So as Matthias said, there are two kinds of microfossils that we're looking for. The first type is foraminifera. They're still tiny, tiny, tiny. They're about the size of a grain of sand, and they're made of calcium carbonate. And because they've got carbon in them, we can use them for something called radiocarbon dating. And that means that we can tell how old the different layers of the sediment are. Now the other kind of microfossil that we use are diatoms. Now diatoms are different, they're much smaller, and they're made of silica. So that means they're basically made of glass. And all these different kind of species of diatoms, they all live in different environments. So some live in the sea ice, some live in very cold waters, some live in open ocean waters. There are even species of diatoms that live in lakes, but obviously we're not interested in those. So what I do is I look at the diatoms down the microscope, identify the different species, and that tells us what's there. So some diatoms, for example, might be in a slide like this.
So overall, what we will do here with all the sediment cores and the geophysical data is reconstruct the retreat of ice onto the Bellingshausen Sea shelf. And this is really important because the biggest uncertainty in predicting global sea level rise today is what's going to happen to the West Antarctic ice sheet, because there are potential instabilities that could cause it to retreat very fast. And here we have the opportunity to really look at how a marine-based ice sheet, an ice sheet with its bed a long way below sea level, really retreated in the past.
So we are focusing on the West Antarctic ice sheet because there are indications that in the past the West Antarctic ice sheet had collapsed, and that led to a global sea level rise of 5 meters. And we know from satellite data collected over the last 30 to 40 years that there are dramatic changes affecting the Western Arctic ice sheet with a loss of significant amounts of ice, especially in the Amundsen Sea, which is located to the west of the Bellingshausen Sea. And there are two major glaciers, the Thwaites Glacier and the Pine Island Glacier, which show the most dramatic ice loss anywhere in Antarctica. And there's fear that this might be the prelude to a collapse of the entire Western Arctic ice sheet. However, as I mentioned, the satellite data, they only span the last few decades, and we need to know also over longer time scales how ice retreated, especially after the last ice age, and to find out how exceptional these rates of retreat observed over the recent decades are. And the Bellingshausen Sea is special because what we might be looking here, that might be the next stage of deglaciation, which is currently affecting the Amundsen Sea. So we can learn a lot about our future development of sea level rise from looking into the past of the Bellingshausen Sea.
So that was it. I hope you now have a better understanding of why we perform our geological research in the Bellingshausen Sea and how it relates to making better forecasts about what is going to happen to the Antarctic ice sheet in our future. I hope you enjoyed it and see you next time.